55, we're going to get into some trigonometric substitutions. So what we will do here is take algebraic expressions and replace them with trigonometric expressions. The idea being that something that we might have a hard time integrating algebraically, maybe we'll have an easier time integrating it using trig. All right, so there's a few different cases that we're going to focus on, but they all involve radicals, binomials contained within radicals to some extent. All right, so the first one involves letting sine of theta equal u over a. Now, it's really just, honestly, if we can kind of pare this down substantially by saying that we're going to define an expression u and another expression a, right, where u is the variable component of your given integral, or a variable component, and a is some constant component. All right, but what we want to do is we want to establish the different ways in which we can relate u and a as the sum or difference of binomials squared. I'm sorry, not binomials squared, monomials squared, creating either a sum or difference of perfect squares, or at least that look. So what we're going to do is work with a reference triangle and just place u and a along that reference triangle in different ways, hoping that we can come up with those relationships, right, those radical relationships. So we'll start with letting u be the vertical side and a be the hypotenuse, all right? Because u and a could occupy any position within the triangle, so why not go for those, all right? If we use the Pythagorean Theorem, as you know, a squared plus b squared equals c squared, we would have an unknown a plus u squared is equal to, well, I already used a. A is my hypotenuse, so let me use something else. I'll use x. X squared plus u squared is equal to a squared. And if I solve for x, I'm going to be subtracting a u squared from both sides and taking the square root. All right, so since we're assuming a first quadrant reference triangle, we would expect this to be positive. All right, and we will be making that assumption. I'll get into why as we go further, but we're looking at a reference triangle that occupies a position similar to this. All right, so that makes our missing side here the square root of a squared minus u squared. All right. So you think about all the different ratios that you can come up with. All right, a little bit of spacing issue here notwithstanding. I'll fix that at some point. All right, we could say, for example, the sine of theta is u over a. We could say the cosine of theta is equal to the square root of a squared minus u squared over a, adjacent over hypotenuse. All right, we could say the tangent is opposite over adjacent. We can get into all those reciprocal functions. Secant, which is really just the cosine function flipped. We could have the cosecant, which is really just the sine function flipped. Or we could have cotangent, which is really just the tangent function flipped. Oops. So all of these different relations would come into play. But what we want to try to do is come up with ratios just for the sake of making things as uncomplicated as possible. We want to develop a ratio of the variable, the simple variable, the u, that we're creating, u to the constant a. All right, that's going to create a linear relation. All right, because u over a
can also be thought of as 1 over a times u.
If a is constant, or an expression made up of constants, and u is a variable, or a simple expression made up of variables, then you're looking at something that should be easily differentiated and integrated. All right, so there's that. Now, when it comes to the other equation, we're gonna develop two equations when we do a trig substitution. The other equation is going to be the ratio of the radical to the constant. So radical to the constant, whatever the radical is in your integrand, the one that you're looking to replace with a trigonometric substitution, that's going to be the numerator, and the constant will be the denominator, and whatever trig ratio that corresponds to is going to be the one that you go with. All right, and again, another spacing issue here. All right, these should be two separate equations. I'll make the edit on that at some point. All right, so that's the idea. So out of all the different possible ratios that we could have come up with, I want the one that's the variable, the ratio of the variable to the constant, and one that is the ratio of the radical to a constant. So that would be these two. All right. The second case places, I mean, if we're looking at it as, okay, what are the different ways in which we can place a u and an a? We could place a u here and an a here. We could place the u here, the a here. You know, but in terms of uniqueness, there's really nothing else. All right, because let's say, for example, I placed, I just did a switch on this. If I placed this here instead of here, right, it would still give the same missing side, just in a different location, right? So there's nothing unique there. All right. The benefit of these three cases is that they incorporate the three most important trig functions, which is sine, tangent, and secant, the ones without the cos. All right, so that's why we select these. You could, if you wanted to, use an arrangement involving cosecant, secant, and cosecant, cotangent, and cosine if you wanted, but it's not going to make things any easier. All right, using the Pythagorean identity, I'm going to kind of cut to the chase here. You get the square root of a squared plus u squared, and the square root of u squared minus a squared. If we're looking again at different ratios, we'd have sine theta, cosine theta, tangent theta, secant theta, or cosecant if you wanted to go with that one first, cosecant theta and cotangent theta, and their corresponding ratios. All right, because remember you have your the six ways in which you could represent the ratios, the ratio of two sides of a triangle. All right, it's really kind of like just thinking back to probability and statistics and things like that. You know, how many ways can you take three things and arrange them two at a time? 3p2, all right, or 3 times 2, which is 6. So there's 6 possible ways. So what do? They just gave a name to every possible arrangement. One of them they called sine, the other they called cosine. That's an oversimplified explanation, but that's pretty much it. All right, as far as we need to. All right, so again, there's a space here. There's a space here, a space, oops, here, and a space here. Formatting got a little out of whack. All right, so the sine function would be u over the square root of a squared plus u squared. All right, again, I want variable to constant. That's not variable to constant. That's variable to radical. All right, cosine adjacent over hypotenuse. That's constant to radical. Tangent we already knew, that's what we used to get started, u over a, so that's a keeper. Secant is adjacent, hypotenuse over adjacent. All right, so that's the reciprocal of cosine.
All right, that's radical to constant. So at this point, you can kind of stop because you got what you need, the important ratios that we care about. But just for the sake of making it complete, reciprocal of sine a squared plus u squared under the radical over u. And then for cotangent, it's just a over u. So then for the last case,
Same idea, just pulling ratios.
opposite over hypotenuse, the square root of u squared minus a squared over u. So that's radical to variable, so no help there. Cosine adjacent over hypotenuse, a over u,
The reciprocal of that would be perfect.
u over a, right? Tangent opposite over adjacent, square root of a squared, u squared minus a squared over a, right? So we got what we need with these. And just to finish it up, cosecant u over the square root of u squared minus a squared, and cotangent a over the square root of u squared minus a squared. All right, so again, all we're looking for is variable to constant ratio, radical to constant ratio. Once you have those,
Then you have the two types of equations that are going to be useful for developing the solution to it, or at least substitutions involving trigonometry.